Welcome to the experiment number 12, peptides and proteins. Peptides are compounds of two or more amino acids connected by a peptide bond. Since you need to complete this lab report and quiz and you didn't start the lecture, I will give you a quick overview of peptides, amino acids, and proteins so you can complete your quiz and report. And then we will go over the report and make sure you can complete it. So let me share now some images so you can understand. Let me see here. Okay, these are some images of, let me see if I find an amino acid. This is proteins. Okay. So we said that peptides are compounds of two or more amino acids connected by a peptide bond. A polypeptide is a chain of 10 or more amino acids. And proteins are also formed from the same building block, the amino acids. So here we have one amino acid, glycine. And here we have another amino acid that is alanine. And we said that when they are connected together, they form either proteins or peptides. The main difference is that peptides are made up of smaller chains of amino acids. When 50 or more amino acids are linked together in the chain, we call it proteins. And here you can see that they are only 20 amino acids, and they are all listed here. The difference between the amino acids is just the side chain. Let's pay attention a little bit at what is an amino acid. Let's look at this, the glycine, for example. What is, before we continue talking about peptides and proteins, we know that the proteins are chains of 50 or more amino acids. We know that the peptides are shorter chains, but let's pay attention a little bit at the structure of an amino acid so you can get familiar with it. An amino acid, let's look at glycine, has a central carbon. Let's look at this. This carbon is called the alpha carbon. And the alpha carbon is bonded to two alpha functional groups. Let's do it in another color. In green is bonded the alpha carbon to the ammonium group, NH3+. And is also bond, I will do it in blue, to a carboxylate group, COO minus. And the alpha carbon is also bonded to a hydrogen. Let's do it in purple. And a side chain that is called the R group. In this case, the R group, the side chain in glycine, is hydrogen. Let's pay attention to alanine. Again, we have the alpha carbon that is bound to the same ammonium group and the carboxylate group, and is also bound to hydrogen and the R group. In this case, the R group is a CH3. So this is the main structure of an amino acid. We said that we have essentially 20 amino acids. Pay attention at what is the common part of all amino acids. Is what it is here in blue. The alpha carbon bond to a hydrogen down, and the NH3 plus and the COO minus. The blue part is identical in the 20 essential amino acids. The only difference is the R group. In alanine is CH3, and we have different R groups, and that is the main difference of the 20 amino acids. So the differences in the 20 amino acids present in human proteins just depend on the characteristic of the group R. Now that you are familiar with the structure of an amino acid, let's go back to the first drawing. When you see that glycine combines with alanine to form a dipeptide, di because it's two amino acids, and the dipeptide forms when the carbonyl group, this we said is the carbonyl group, in the glycine bonds to the nitrogen atom in the NH3 group of alanine. So the amino acid on the left, which is the glycine, has a free unbonded NH3, and it is called the N-terminal end. Let's pay attention here. When you see a free NH3 plus, is the N-terminal end. The amino acid on the right, which is alanine, has a free unbonded COO group, and it's called the C-terminal end. This is the N-terminal end. These are the main names that you will need to remember. And what is a peptide bond? We said at the beginning that peptides are compounds of two or more amino acids connected by a peptide bond. What is a peptide bond? It's an amide bond. Let me mark it here. This in red is the peptide bond between the amino group of one amino acid and the carboxylic acid of another amino acid. And when the bond forms, there is a loss of water. If you pay attention here in this graph, the carbon that has the carbonyl group is losing one oxygen. And the ammonia from the alanine is losing 2 hydrogens. That's how they form the water. And the carbon that has the carbonyl group is going to be bound to the nitrogen of the ammonium group. And this in red is the peptide bond. This is how the individual amino acids are connected to form peptides or polypeptides or proteins. Very good. So now we know that there's here, you will see 20 different amino acids. And depending on the R group, you don't need that now. We are going to name them as non-polar amino acids, or polar neutral amino acids, or polar acidic amino acids. The only difference is the R group that is marking these drawings in yellow. Now that we know the basics of amino acids, and let me show you how are we going to name the amino acids. So pay attention to this peptide. We have a bond between amino acid, it comes from alanine, the second is glycine, and the last one is serine. And this is a tripeptide. How do we name peptide? Very easy. Always look for the peptide bond, right? When you are trying. And we said from the carbon of the that holds the carbonyl group to the nitrogen of the ammonium group. So this is the peptide bond, and this is the peptide bond. And we have a tripeptide because it has 3 amino acids. And we start at the N terminal. This is the N terminal, right? On the left. We start from the amine of the N terminal. What is the amino acid that the name of the amino acid is alanine? And we replace the INE from the alanine in the amino acid with YL, alanyl. So we start from the left and we say alanyl. We do the same with the second one, glycyl. Instead of glycine, we say glycyl. And then the last amino acid retains the name. So the last one is serine. We keep the same name. So we start from the left. So the name of this tripeptide is alanyl, glycyl, serine. The last one keeps the name. And here we have an abbreviation of each amino acid. And that you can see in the page that we have seen at the beginning. You can look at that page and you will see that glycyl, the abbreviation of glycyl is GLY. From alanine is ALA, and each amino acid has a abbreviation name. So let's look at here. We have a dipeptide here. Again, we start from the left. So let's look at how do we name this dipeptide? We start from the N terminal, the left. We start from glycine and we change the INA end by YL. So instead of glycine, we say glycyl. Glycyl, and the last amino acid retains the name. So the name of this dipeptide is glycylalanine. Very good. What happens what is hydrolysis? We can have a dipeptide. Let me see if we have a drawing here, an image of here. Okay, let's share this page. Let's look at the bottom. We have a tripeptide. And this is what happens. Look at the bottom. When there is hydrolysis of the tripeptide. Hydrolysis is the addition of water across the peptide bond. This is the peptide bond, and this is the peptide bond. So basically, we are restoring the original amino acids. When we have a protein or we have a peptide, and we hydrolyze that, we add water across the peptide bond, producing the individual amino acids. This is a slow process. So in the lab, the amide bonds or the peptide bonds are hydrolyzed under acidic or basic conditions, and we need also strong heating. In living systems, like in the body, the peptides are hydrolyzed with enzymes. So that's why here it says if we treat a tripeptide with an enzyme, we add water across the peptide bond. So let's look at the peptide. If you have to hydrolyze, what is going on? If we look at here, how can we form the individual alanine? We just add one oxygen to the carbonyl group and two hydrogens from the water will bond to this nitrogen. So let's make it in red. If we break this, the nitrogen will add two hydrogens from the water to the nitrogen and in another color, one oxygen, and we are restoring the individual amino acids. Same thing happens when we break this peptide bond. So we recover alanine, lysine, and serine. Very good. What else we need to learn about this lab before you are ready to go to the to complete your quiz and report? One more thing about proteins. Let me share here another drawing. Look at the drawing on the bottom. We say that proteins, this is a protein. We say that protein form when 50 or more amino acids are connected together. And there are 4 levels of protein structures. The first one, and this is, remember that, we have 4 levels of protein structures. The first level is the primary structure. The primary structure, we said that there are many amino acids bound together. Okay, so the sequence of the amino acids in the polypeptide chain will make the primary structure. And the function of a protein depends on the order of amino acids in the chain. So it's not the same. For example, in this dipeptide, if the glycine comes first or the alanine comes first. So the order of the amino acids in a protein makes the primary structure. The secondary structure, so here is what you are looking at the bottom, is the secondary structure. The secondary structure, in this case you see a helix. See this shape? And has a coil shape. The secondary structure depends on the folded structures that are formed. In this case, we have a helix. So the oxygen atoms from the carbonyl groups and the hydrogen atoms from the amide group form hydrogen bonds. So you can see here the hydrogen bonds. The R groups do not participate in the secondary structure. Only the, as I just said, the oxygen from the carbonyl group and the hydrogen from the amide groups. And we can have 2 different secondary structures. This one at the bottom is the alpha helix that has a coiled shape because the hydrogen bonds are between the oxygen of one carbonyl, it's hard to see in this drawing, and the hydrogen from the next turn of the NH group. So that's why the secondary structure is an helix. You can have an helix, or you can have this structure right here that is called a beta pleated sheet. Basically, hydrogen bonds form between the peptide chains. So these are 2 examples of the secondary structure. It said it's hydrogen bonds, but the R groups, the side chains, are not participating in this bond. It's just the oxygen from the carbonyl and the hydrogen from the amine. And they will form these 2 different that we saw structures. And then the third level that we have a tertiary structure. The tertiary structure will give you the overall 3-dimensional shape of the protein. And this is the result of the interactions between the side chains, what we call the R. The attractions and repulsions between the R groups will make the chain to twist or bend until the protein form a specific shape. And there are many kinds of interactions. Can be sulfide bonds or salt bridges, but we are not going to get in too much detail, as you just have to complete, as you didn't see this in lecture yet. So we said about the four structures, and we talk about the primary, the order, the secondary structure, the the tertiary structure, and here in this drawing, you can see a triple helix. This is the quaternary structure. It is found in proteins that have more than one polypeptide. You can see here the different, you have the three different colors, and the different subunits are held together by the same interactions that stabilize the tertiary structures. But you need to have more than one polypeptide. For example, hemoglobin is a protein that transports oxygen in the blood, has 4 polypeptides in the chain. So overall, let's share here, just as a review, you have the primary structure, that is the order here, just the order. Where is the peptide bond? Can you find it? Can it be this one? So the order of the amino acids will give us the primary structure. And then we see two examples of the secondary structure. We see this one or this one, the helix. And then the protein, depending on the interaction of the R groups, will form the overall shape of the molecule. And we said that that is depending on the attractions and repulsions of the between the R groups. And then the last quaternary structure, here, you need different subunits that are held together in order to form that quaternary structure. So now you have an idea about proteins, and let's see what are we going to do in the experiment, in this, what are we going to explore? First of all, we are going to look at the properties of proteins. Let me see here. The first thing you are going to do in the lab is denaturalization. What is denaturalization? It happens when a change, let me draw here. When a change, it can be a change in conditions. We can increase temperature or make the pH very acidic or very basic, or we can add an organic compound or heavy metal ions. We will disrupt the interactions that stabilize the secondary, tertiary, or quaternary structure. So, and that then is, when we do that, we disrupt the interaction that stabilize the second, tertiary, or quaternary structure will make the protein to lose shape, and it will be biologically inactive, and they will look like a wobbly piece of pasta. Remember, when we do denaturalization, the primary structure is not affected. So the order of the amino acids in the protein is not affected, just the secondary, tertiary, and quaternary structure. So this is the first thing we are going to do. What else are we going to test in the proteins? The solubility. Let's look at glycine here. When is the amino acid or the protein more soluble or less soluble? The solubility will depend on the pH. pH, you remember, is the concentration of hydrogen. The concentration, the pH, is the minus log of the concentration of protons. So depending on the concentration of protons, if the protein will be more soluble or less soluble. If the pH is near the isoelectric point, what is the isoelectric point? Is when the number of positive and negative charges is equal. You can pay attention that here we have a plus in the ammonia, and here we have a minus. So if the positive and negative charges are equals, the proteins are the least soluble because the attractive forces predominate between the protein molecules. What happens if the pH is above the isoelectric point? Let's say is basic. What does it mean that is basic? We have, when it's basic, the concentration of hydroxide is higher than the concentration of protons. This is basic. What happens when we have a lot of OH? Think about it. The molecules will exist as anions, negative ions. Why is that? The OH will combine with one hydrogen in the ammonia, and you will have basically, instead of the glycine, NH3 plus, you will have NH2 this is hydrogen, and here COO minus. It will exist as a negative ion because the OH minus will combine with one hydrogen from the ammonia to form water. And what happens if we have an acidic pH? Let's look at an acidic pH. An acidic pH means that the concentration of protons is higher than the concentration of hydroxide ions. And then the molecule will exist as a positive ion. What we are going to have in that case is the molecule basically what happens is that it will combine with the acid. And when the molecules have a charge, they are more soluble in the water. So if the pH is either too basic or is above the isoelectric point, or less acidic, the pH is lower than the isoelectric point, we will have ions, positive or negative, and then the molecule will be more soluble. So in this experiment, we will isolate the protein casein found in milk by adjusting the pH and let it fall out of the solution. Once we have the solid, we will determine the percentage of casein in milk by weighing a sample of milk and then weighing the amount of casein that we isolated. This is the experiment we are going to do to test the solubility of casein. And then we will do 3 chemical tests. So let me share the page of the experiment. Okay. So let's look at the experiment. The last part that we are going to do is 3 tests. Let's look at the chemical test and then we will go over again. The last part of the experiment is the chemical tests. Only 3 tests, as you see here. Burette test, anhydrine test, and here, xanthoprotease test. The first one, the burette test, is to test if you have a peptide or proteins with 2 or more peptide bonds. So basically, the single amino acids or dipeptides will have a negative reaction, but all the others will be positive, and the color will change from blue of the copper into violet. So in this case, violet we said is positive and blue is negative. The next step, it detects basically most of the amino acids and proteins. But the amine, I don't want to get much into the chemistry because you don't need at this level of non-major, but you need to know that secondary amines will give a yellow color. The amino acids will produce a blue-violet color, a purple, let's say purple here. You need to have a primary amine or amino acid, and then hydrine will form the purple color, a chromophore, with a primary amine or a amino acid. A negative reaction will be colorless. The solution will be colorless. But in this case, we have a yellow. That is because some of the amino acid or some of, for example, proline is a secondary amine and will give you a yellow color. And then the last test that we are doing is just to detect amino acids with an aromatic ring. And a positive reaction is a yellow color. Negative reaction is a clear color. And if we share, we saw, let me share one more time, so you know what this test is about. When you look at the 20 amino acids here, and you look at the side chains, for example, which one has an aromatic ring? This one has an aromatic ring. And this one has an aromatic ring. So then they will test positive in the xanthoproteic test, the last test that we are doing. So now that I gave you a quick overview, so you have an idea of what are amino acids and proteins, let's go over the report that you have to complete. The first thing that you will have to complete here is to draw, it says, the structure. Draw the condensed structure of the given amino acids, peptides, and reactants and products. You have the page of all the 20 amino acids. So you remember glycine has the alpha carbon bond to the NH3 plus. On the other side is bond to the carboxylate, always bond to a hydrogen, and the R group is a hydrogen. That is glycine. How about serine? Serine, you have it in, if you look at the PDF, you will see that the side chain is a CH2 OH. You have it in your PDF. And here is always the same. The alpha carbon bond to the ammonium group, bond to the carboxylate. Very good. What happened? You have to draw glycylserine. We start from the left. So if the first name that you see is glycyl, we start at the N terminal. So we are going to write the glycyl first. That means that it comes from glycine. So if you want to draw the dipeptide, you start from the left. And what happens here? Instead, we said that we are going to remove one oxygen because, and we are going to remove two of the hydrogens. So we are going to bond this. This is the peptide bond. We remove two hydrogens from the second amino acid and one oxygen from the first one. And then we continue just with the serine. That keeps the same name. And for the next one, serine-glycine, you do the same, but you start with serine. First on the left, serine, you remove the oxygen and you bond it to the glycine. Very good. And then it says draw a condensed formula of the reactants and products for the hydrolysis of cerdyl glycine. So if you write cerdyl glycine here, the way I explained, what are you going to have? What are the products of hydrolysis? If you treat it with an enzyme, again, you get the original amino acid. So you draw serine and glycine. And let's look at the next one, cerdyl glycyl alanine. So that is a tripeptide. If cerdyl is first you draw the amino acid, you will, after you treat it with an enzyme, you will obtain the original amino acids with our serine, glycyl, and alanine. Very good. So this is the first part. I can actually do one. Let's do this one, cerdyl glycyl alanine. If we have to draw this, we start with serine, right? Very good. And we have, this is the peptide bond, and we are going to bond it to glycyl. So we are going to have NH, glycyl, the R is a hydrogen, and then we have another peptide bond. Bond to, again, the alanine. And you have the 20 basic amino acids. Very good. So this is the cerdyl glycyl alanine. What happens if you treat that with an enzyme? You obtain the individual amino acids again. So then you will write the serine plus the glycine plus the alanine. Very good. What do you have to do next? Let's look at, it says denaturation. Let's look at that, denaturation. Observations seen in the lab are indicated in the highlighted cells in the table. So whatever you see in blue is data given. You were supposed to do it in the lab, but because it's virtual, you are given the data. So you will read the procedure so you know what you are doing in the write-up of the experiment. So what does it mean if it's cloudy? When you applied heat, read the write-up, when you applied heat to the protein, we said it lost the shape, except the primary structure. and the interactions stabilizing the secondary, tertiary, and quaternary structure are disrupted. And that's why you see cloudiness. If it's clear, there was no denaturation. So that is positive, and you will explain. If you add acid, again, same thing. Look at base. We said it says clear here. So the protein stays clear, is indicating that it is maintaining the original shape. Means no denaturalization occurred. But making the pH very basic should be positive. So here either they didn't add too much base or somehow it says clear. The observation indicates that there is no denaturalization. Semi-cloudy. There was some denaturalization. But you are treating this with alcohol. It's another way. But the process takes longer with alcohol than it does with heat. So the solution was somehow denaturalized in less scale. And then what happens with heavy metal ions? Yes, it says cloudy, it was positive. And that's basically what you have to explain. The next step is testing the solubility of a protein. So you have to pick somehow, they give you a range of values, you pick any value. So for example, what did you do here? You weighed the milk, then you changed the pH, adjust the pH, you made it solid, and once it was solid, you weighed it again, the protein. So let's say you pick 45. The mass of the beaker is 45, and the mass of the beaker and milk is 60. The mass of the milk will be 60 minus 45. Let's say we have 50 grams of milk, 15 grams of milk, 1, 5. pH of milk, you pick it from here. Let's say you pick it 5. The protein becomes insoluble between 3 and 5. That means that the isoelectric point is between 3 and 5. So let's say I pick 3. And then they tell you the mass of the watch glass. Let's say I pick 20, and the mass of the watch glass and the casein is 23. If I want the mass of the casein, it will be just 23 minus 20. And in my case, it will be 3 then, 3 grams of casein. And then they ask you, how do you calculate the percent casein in milk? You know what is the percent. In my case, the percentage, it will be 1. The percentage of casein, it will be the mass of casein that you weighed, 3 grams, times 100, divided by the mass of the milk. In my case, is 15 grams. So in my case, with my data, I have 20% of casein protein in the milk. This is what you need to do, and next, you do the chemical tests. This is the last part, and we went over a little bit For example, let's look at you have glycine, tyrosine, gelatin, egg albumin, and casein. Let's look first at the burette test. What did we say? It's blue. What does it mean? Glycine gives a blue color. It's a negative test because we know that single amino acids or dipeptides have no reaction. Same thing with the next one. And then when you see violet, it's a positive reaction. The change from blue to violet indicates a positive reaction. And then let's look at the next test, anhydrine test. What did we say? Purple is positive test. When it changed from clear to purple, that means we are in the presence of primary amines or amino acids that have a hydrogen atom on the alpha carbon to the nitrogen. But what you need to know is that purple is positive. What is yellow? Here. Is it positive or negative? Negative will give you a clear, but it's still actually an indication. Secondary amines, for example, proline, makes a yellow color when treated with anhydrine. And how about the last test? What does it mean clear? Clear is a negative test. What are we testing? This test detects amino acids with aromatic rings. Clear means no reaction, negative. If we have an aromatic ring, it's a positive reaction, and we see a yellow color. And that indicates the presence of an aromatic ring in the amino acid. And this basically concludes this workshop. It says give your feedback on what went well, what you learned, and what you could improve. Think about when the lab report or the lab data is giving you a negative and you were supposed to receive a positive. For example, when you did denaturalization with a base and it stayed clear, is that right? What were you supposed to do? Maybe you need to make the pH a little bit more basic. What happened with the alcohol? For example, that it was maybe too slow and you didn't wait enough. Think about those things to complete your report. And this is it for this experiment. I want to thank everybody for listening to me. And thank you again. This will conclude this workshop.